All right, so we're going to talking about our database project today, and we decided to focus on a Seattle coffee shop and create a database for that. So I'm Carson.
I'm Sean.
I'm Claire.
And yeah, we're going to tell you a little bit about our database. So why do we choose this topic? So coffee is a pretty central part of Seattle culture, and there's a lot of cafes and coffee shops around the city. So we thought it would make sense to kind of design a new chain that kind of follows some of uh, the ideas that we can learn from those coffee shops. And so we thought those would be good examples for us. So, and then coffee chains also require a lot of different types of data and a large amount of data. And so we thought that that would make a good source of a database project is to design a database for something that needs a lot of physical location data because a coffee chain has multiple locations. It needs a customer and employee identifying data, um, order data, and for determining what items are sold, and image data and text data for when you're in a store and you see maybe a TV that has images of the products and data describing them, like text describing them. We need to store that type of data and other data as well. So here's our ERD. We have 9 entities that we included, and we'll go over some of them more in depth in the later slides. But yeah, this is our overall ERD. So for the location to employee entities, these represent the relationship between every employee in the database and every location in the database. And of course, every coffee shop location needs employees. So that creates a one-to-many relationship because employees work at these locations. However, new locations might be added to the database before they open, and that's what the optional on the many side means, because there may not be any employees added to this location, but there definitely will always be a location. So there might be a location that has 0 employees, but there could be some locations might have 20 employees. It can go from 0 to 20 or however many employees you might want in a location. So that's why there's the optional relationship on the many side. And then for the data types, we have the IDs for the location employee both marked as ints because they need to fit into a individually identifying format. So then also that's why they're marked as row numbers in the database to ensure integrity. And then as well, a foreign key, I forgot to mention, it's a foreign key of location ID is included in the employee table to create the connection on the many side. But yeah, and so all these IDs are marked as integers, as row numbers. And then zip code is stored as a variable character of our car because no calculation is necessary for zip code, and also LS for leaving zeros. Latitude and longitude require precise decimal values, and so we included floats. We chose to use floats because those go up to 7 decimal places, which is probably enough for really any latitude or longitude number you'll need. And then lastly, wage is stored as a decimal with a decimal 10-2 right here. And because cents, the second number, only requires 2 places, and so we thought that 10-2 made sense because you will only ever need up to 2 places for the wage. And then for the data query, our first data query, the query calculates the total sales facilitated by each employee and the number of orders they've handled. So it selects the employee ID, the first name and the last name, and then it counts the total number of orders handled and the total sales facilitated. And takes that from the employee table. It joins with the order table and the order itemized table in order to get the order data and the quantity data. And then it groups by the 3 identifying characteristics, the employee ID, first name, and last name. And then orders by the sales descending. And then this is important because this might be useful for determining who deserves a raise, because if someone has facilitated the most orders, then they might deserve a raise more than someone else. So it's useful for that. And on to the next group of slides.
Okay, so I'm going to be talking about the order itemized, and item entities. So in with these three tables, the order itemized is an associative entity. So there's two one-to-many relationships with the many sides both pointing to the order itemized. And the business rule for these is that each order can contain multiple items, which is tracked in order itemized, the associative entity. However, every entry in order itemized can only be associated with one unique item at a time, which is tracked in the item table. And then for some of the data type decisions that we made for these, we made all of the IDs integers because we're using them for primary and foreign keys. And there's no need for a double that would require decimal places. And these IDs are being used to identify unique records within each entity, which allows for data integrity. So if we wanted to ever expand on this database and add more tables, possibly, we have these IDs that we can use as keys to link these tables and create relationships between them. And then for price, we specified price only taking 2 digits after the decimal point because that's the format that money usually follows. And we did not use the money data type for price because the decimal data type is more accessible across different database systems, whereas money is a SQL Server specific data type. Next slide, please. And so for this data query, we're looking at sales summary by location. And so we're taking the orders table and joining that with the location and order itemized tables to select each individual store and compute the total sales, number of orders, and average order value for each of these. And this is important for stakeholder decision making because it provides insights into the performance of different store locations, which helps with decision making, with resource allocation and marketing efforts. So you can see which stores are performing well and which ones are underperforming, and you can take action in that way. And overall, being able to see this data allows you to assess the overall financial performance of the business and make decisions based off of that.
All right, and now I'm going to talk about the customers to rewards entities. The type is one-to-many, and this is because a customer can accumulate and spend rewards points through various transactions at the coffee shop chain, which are tracked in the rewards table. And the business rule is that each customer can have multiple reward entries, but each reward entry is associated with only one customer. In terms of integrity constraints and data types, for the customer table, customer ID is the primary key, ensuring each customer has a unique identifier. Email is constrained to 50 characters to accommodate typical email address lengths, while ensuring enough space for most use cases. Phone number uses varchar instead of int to handle different phone number formats, including those with special characters like dashes or parentheses. For the rewards table, rewards ID is the primary key, ensuring each reward record has a unique identifier. Customer ID is a foreign key linking the rewards table to the customer table, ensuring referential integrity. The total rewards earned and total rewards spent uses a decimal data type to accurately represent financial values and ensure precision for currency calculations. For data type decisions, email uses varchar 50 because emails often contain special characters and vary in length. Varchar is used to accommodate these variations, and 50 characters is sufficient for most email addresses. For phone number, we use varchar 50 as well because phone numbers can include country codes, spaces, dashes, and parentheses. Using varchar instead of int allows for these formats and ensures the integrity of the phone number data. For rewards earned and spent, we use decimal 10-2 because financial values require precision and accuracy. The decimal type is used to ensure values are stored correctly without rounding errors, and 10-2 provides sufficient range and precision for typical reward points and transactions. Next slide. I'll be going over the data query customer rewards summary. This query calculates the total rewards points earned and spent by each customer. It helps in understanding customer engagement and loyalty, which can inform marketing strategies and rewards programs. This query selects customer ID, first name, last name, total rewards earned, total rewards spent, and net rewards, joins customer table with rewards table to match customers with the rewards data, groups by customer to calculate total and net rewards, in orders by total rewards earned and in descending order. The implications are that it identifies loyal customers through rewards data, allows for special promotions to high net rewards customers, and assesses the balance of rewards earned versus spent. These insights help stakeholders improve customer satisfaction, optimize the rewards program, and drive business growth. Moving on to the last slide, some challenges we faced included ensuring data is clean and consistent before insertion. Inconsistent formats and missing values require extensive cleaning. Also, choosing the correct data types to balance performance and storage was a learning curve. For instance, using varchar for phone numbers and emails to handle various formats. Through this, we learned to invest time in designing a robust schema and anticipate potential data variations and edge cases to minimize future adjustments. Also being prepared to adjust schema definitions as new data insights are gained. And that's the end. Thank you.